Hello, I hope you are all doing well. Today I'm going to be talking about some lightning physics. Um, this is going to be more of a qualitative discussion on the physics behind it, how they work, what's the mechanisms behind it, to give a better idea, and I'm going to link some resources down below in order to help if you find this interesting and would like to explore further. So I'm first going to be talking about what you would normally see on how lightning is explained. When you look up online, gamma radiation has also been observed from lightning ignition from NASA, and some problems and questions that arise from this, what this means and how this is not the full picture of how actually lightning occurs. From this, I'm going to try to rectify that by going a little bit further into runaway electrons, and then the relativistic runaway electron avalanche, RREA, as a way to explain how lightning can occur from its start to its end, and also some hydrometers. So there's a lot of moving factors with lightning, as with many of these physical sciences, and this would just give another reason as to how lightning can occur, how this chain reaction can occur, and another way, so that another thing that you can potentially explore if you so choose. As I said before, this is more so just a introduction to the field, get you interested and excited about this. So we first off with just basic introduction, as shown in this picture. Essentially, when you normally look this up, the people talk about how warm air rises, you'll have cold, denser, like ice crystals will fall, and then this essentially exchanges electrons. As you can see in this picture, warm air rises, cold air sinks, and then this will strip off electrons in exchange. Then this leads to where negative charges are on the bottom of the cloud, positive charges at the top. This leads to like that stratified charge, which builds up the electric field, similar to that of a battery. Another place that can have positive charges is the ground, compared to the bottom of the cloud. This then builds up until it overcomes the insulating properties of our atmosphere, and then lightning strikes. So some interesting things is that terrestrial gamma rays, the NASA NASA Universe Web team in 2023, they recorded gamma radiation, or they published it in this article, where they talked about where Fermi, I believe, recorded terrestrial gamma rays from lightning ignition along the equator, and this is quite interesting. I highly recommend looking up at the picture for this. But this leads to an interesting question. So gamma radiation needs require high energy, and so this explanation right here doesn't really explain how it reaches such high energy. So this kind of brings up a question: why? I mean, there's exchanges of electrons from just hot air rising, cold air sinks all the time. Why is it producing gamma radiation? So some questions from this. So let's bring up some questions. How are these electrons behaving? Why are they producing? Why is this producing gamma radiation? As I said before, why are they moving so fast? Because radiation is caused from acceleration of charges, such as an electron. Why terrestrial gamma rays? Why is it producing this? Why such high energy? For example, if I were to make a basic circuit, have a current go through, so electrons moving in this current, that will not turn me into the Incredible Hulk, aka it will not give me gamma radiation from just a basic circuit. That requires a lot more energy. Where is it getting that? Where is that happening? And also, what is the emission mechanism for this radiation? So, we now have some questions. Let's try to answer them. And we're going to be answering them in this thing I like to call or is called the runaway electron, which I'll just say RE for right now. So this was first described by Wilson, TGR, in 1925, I believe, from his cloud chamber, which was made in, I don't know, that was made in about 1911, 1912. And essentially, a runaway electron is an electron that undergoes free fall, acceleration, into like relativistic like particles. So it travels close to the speed of light, essentially. And this is, or is believed to be caused from background radiation. So what excites these electrons to undergo this super high acceleration, background radiation, and this can be from, interestingly enough, some sources would be cosmic rays, or radioactivity, and potentially some other sources, where essentially these can excite the electrons, and this is from where they ionize the air, potentially causing ionized air, free electrons that can then collide with other particles and also have the chance to increase. So these can collide with other particles, other free electrons, even the nucleus, as well as potentially increase the electric field, which we'll talk more about. Also, what does it mean to ionize air? That just means that the electrons are stripped away from their nucleus, creating free electrons. This is also another state of matter called plasma, which I'll even write, to plasma. Quite fun. But we, of course, when these electrons are colliding, when they're hitting with each other, they're not always creating other runaway electrons, which is why we also need to talk about secondary electrons. And these can be from colliding electrons or from just ionizing the air. So this can be from colliding runaway electrons, or just ionization of air. And these also, they greatly outnumber the runaway electrons, which just makes sense, just conservation of energy. One particle hits another, it probably will not have the same speed as the particle that originally hit it. And also there's just so many ways that you can lose energy within this. You aren't always going to become a runaway electron. But what does this mean? These are low energy electrons. They're below the energy threshold, which we will talk further about. That can cause the RREA. And they lose energy fast. This can further ionize the air, creating other free electrons, and also increase the electric field, which is really important because as you're increasing the electric field, you can then cause other electrons to gain energy, becoming secondary electrons or just runaway electrons, which then further collide or create or strengthen the electric field. So as you can see, this then turns into like a chain reaction. And this then leads to a RREA, relativistic runaway electron avalanche. So essentially with the buildup of the electric field, the E field, increasing runaway electrons, further ionizing the air in thunderclouds can lead to this type of chain reaction, RREA, which would then potentially cause the lightning. For this to happen, this would mean that the energy loss from frictional forces, ways to lose energy, in the medium has to be less than the average rate of energy gain from the electric field, which seems pretty straightforward. What does this mean? Well, let's look at this graph I just looked up. So right here on the Y, we have the frictional forces. It's in log. You can actually see it in this paper right here from Dwyer 2004, which I will link. But essentially, this is the frictional force or the energy loss. So the higher up you go, the more energy you are losing. And as we can see on the x-axis, this is the kinetic energy. So as you are going further to the right, you are increasing kinetic energy, you're increasing the energy in this system. So let's look at this a little bit further. What we have seen from various experiments is that the frictional forces are going to increase until it reaches essentially this critical energy level, and it significantly decreases, and then it will reach this E threshold. I also named this as above as ETH. This is the energy requirement in order to have an RREA to occur. So as we can see, as the kinetic energy increases, as it reaches that critical energy level, it significantly reduces the frictional forces as the electric field is increasing. And then as we can see, the E loss within the medium has to be less than the average rate of gain from the E field. So this leads to that chain reaction. And then, that of course means you're increasing the electric field, you are making more runaway electrons, you're making more secondary electrons, would then make more runaway and increase the electric field and further ionize. That leads to the buildup of the electric field. This will then overcome the insulating properties of our atmosphere, or potentially can, and then we see lightning just like above, but now we know a bit more on what is the mechanism that causes this. We know a bit more on why terrestrial gamma radiation. Well, these are becoming relativistic. These are very high energy, and as we know, as charges accelerate, they release radiation, charges, or electromagnetic radiation specifically, and this is what's causing these gamma radiation when you have such high amount. And so let's do a recap with here. So these background radiation can basically create seed electrons. These are just like the initial electrons that are like runaway electrons that are created from background radiation. I'm just going to call that BR. These electrons then collide with other particles. They also collide with the nucleus as well. That causes some other complications with the math here. This then create other runaway electrons and secondary electrons, further ionizing field, air, and increasing the electric field. We then see that this continues. Potentially creating an RREA, and then it will overcome insulating properties, or potentially overcome insulating properties of the properties of our atmosphere, and then cause those cause lightning, and then from there we can then see those terrestrial gamma rays. Great. So I told you before I would talk a bit about hydrometers. Basically, the problem with background radiation is that it may be too infrequent to ionize the air. As I said before, there's a lot of ways that you can lose energy, frictional forces within the cloud, outside, that this chain reaction just essentially does not occur. So potentially too infrequent. So we also know that most lightning happens in thunderclouds. Well, clouds are made of water vapor, heavily condensed as well. Sorry for my writing on there. Is that important? Well, it seems like, is this a coincidence? Well, quite likely not. So hydrometers, which are like hail and water droplets, may actually help this process to occur. They may help not lose energy within the system, continue the allow for these seed electrons to occur or to continue. So since this is getting a bit long, I will leave it at that, but this is a topic that I highly recommend looking into, and this then brings it off with, this was my talk on lightning. I hope you enjoyed. I hope you enjoyed the going into this qualitative physics of the lightning and what that means and how cool it is. Thank you for watching. Please let me know if I made any mistakes. And